Start. Welcome to the inaugural Robert P. Sharp lecture. My name is Mike Ellis, and I am the chair of the Earth and Planetary Surface Process Focus Group. Let me say a few words first about why we're calling this a Robert Sharp lecture. Robert Sharp, to us in this community, our community, is a Renaissance man, or Renaissance man, depending on where you come from. He became engaged in a very, very broad range of subjects that now fall under the umbrella, the rubric of Earth and planetary surface processes. So he looked to planets. He was doing things at the same time as the Apollo program and had that immediate motivation. He thought about surface processes. He developed that field, or our community's field, with tenacity at Caltech when he was there during the 70s. He thought that fieldwork was extremely important and the fundamental importance of observations. And this photograph shows him in the field, of course. So it is very appropriate that we name this named lecture after Robert Sharp, in that he represents an inclusive community, not an exclusive community. The beginning of this tradition of selecting somebody from the community to give the Robert P. Sharp lecture is going to be the following. We will select one of the two award winners from the EPSP community. If you spent the last hour in this room, you already know that the EPSP focus group gives two awards now. One is a G.K. Gilbert Award, which went to Bill Dietrich, and the other is a Luna B. Leopold Award, which went to Doug Jerolmack. I have just discovered, by the way, that I think I'm the only person who says Jerolmack. Everybody says Jerolmack. Well, we all know his real pronunciation is Ellis. So it is, I'm about to introduce Doug Jerolmack to present this lecture, and it is with a great honor that I do that. And I think if you have not seen or heard a Doug lecture before, you will be greatly entertained. Before he comes up, I want to remind you, please, that sitting on the desk here are the two gilt-edged certificates of the Gilbert and the Leopold Awards. They are sitting on the desk with a pen, because I would like each of you, if you desire it, to sign the back in a small signature, because we have hundreds to collect. So you can come up after the lecture. We have this room until 6 o'clock.
And I'm going to go that long.
In fact, my session follows at 4 o'clock, so it'd be nice if some of you could stay for that too. And in any case, the point being that we have basically this room for a long time. There'll be plenty of time for discussion. And I could just rabbit on and on and on, and we could postpone hearing about noise is the new signal, but we won't. So please come up and sign these when you get a chance. Now I will introduce Doug. Doug, please come to the podium and do what you do best.
I think what I do best is this sort of thing. Just to address Mike's comments, probably a lot of you have never seen me talk before, but I would be surprised if any of you have not heard me talk before, maybe from many poster aisles over. So I'm just going to apologize for that now. No, this is it's a PDF. So I want to do that so I can advance it with this up here. So I'm going to save my acknowledgements until afterwards, but many of my colleagues and also a lot of people in the field that I've not yet met, but whose work I'm incorporating into this talk will recognize their work in here. And so I just want everybody to be aware that there are going to be acknowledgements throughout as we look at the sorts of work, a kind of feeling that's been building in the community that, you know, there's a lot of variability in sediment transport. There's a lot of variability in the shapes of landforms. There's variability everywhere we look. And I think a kind of tradition is to average out that variability in some kind of way. And I think since the beginning of my graduate school career, I've been wanting to, as David Morrig said to me, celebrate that variability. And so this is going to be a kind of talk about celebrating variability. Okay, did that advance anything? No. Do I have to do this? All right, this guy. So, when we think about evolving landscapes, one of the first things that comes to mind is building geomorphic transport laws. And in this talk, I'm going to refer to geomorphic transport laws as phenomenological equations. And they're phenomenological in two senses. First of all, they're phenomenological just in the sort of way that we say we want an equation that captures the phenomenon of interest so that we can understand, say, the evolution of landforms over a long time. They're also phenomenological in the sense of, if you think about statistical mechanics, the macroscopic equations that describe the mean field behavior of systems are often called phenomenological equations. And so the phenomenological equations that we use, some of them are well grounded in physics, many of them are partly grounded in physics and partly grounded in empiricism, but all of them have the goal of trying to relate sediment transport rate to something that we can measure in a landscape, or to try to relate erosion or deposition rate to something that we can measure in a landscape. And so we have things like hill slope diffusion, the linear transport law or its nonlinear cousins. We have the stream power incision law and various other equations like it, which try to relate sediment flux to things like discharge or drainage area as a proxy for discharge, and the slope. And we have a lot of really new, great emerging work on bedrock erosion by abrasion. And I'm just giving one particular reference of that from Leslie Shee's work, where you might want to relate erosion to, say, the actual impact of grains and the rock that is removed during that process. And so one thing about these equations is that we know that these equations average over some sort of time and space scales. Sometimes those time and space scales are very well defined, and other times they're not. And I think it's incumbent on us to start to think about what the length and time scales are that we need to average over in order to start applying phenomenological equations, and we've done this in some cases and not in others. Oh yes, it's this one. Okay. So one interesting phenomenon, or one nuisance, depending on which way you look at it, is that everywhere we look we tend to see a kind of scale dependence in rates and fluxes. And so, for example, this is work from Paulo Passalacqua et al. If you look at a landscape evolution model, you just use a simple nonlinear erosion equation that captures the basic effects of gullying. For example, what you find is that depending on the resolution of the numerical grid, you get different amounts of sediment transport, different quantities of erosion, and you also get a different level of dissection within the landscape. I think my pointer's kind of died out. There it is. Right? Then if we look at, say, real measurable rates of, say, bedload transport, if you stand in a river with a Helly-Smith sampler and you get a sediment trap and you see how much sediment you capture in a minute, and then you see how much sediment you capture in 10 minutes and in an hour, what you find oftentimes is that the mean sediment transport rate is not stationary. Even the mean flux of sediment that you try to measure with a sediment trap can change with the amount of time that you measure it over. And so what determines that sort of scaling, and what determines the limits of that scaling range? Clearly this doesn't go on forever. Eventually we're going to converge on some mean, I think. And another example is just this kind of classic example that I call the Sadler effect, not because Pete Sadler was the first to observe it, but because he's developed this idea richly, which is that in pretty much any environment that we can find, if you plot the deposition rate measured over some interval, which is the thickness of some body of sediment between two dated horizons, and you plot that deposition rate against the interval of time over which it's measured, you typically find that the deposition rate decays with increasing time interval, and it often decays as some sort of power law. And this power law scaling likely contains the signature of stochastic sediment transport dynamics. So maybe even to understand long-term depositional behavior over thousands of millions of years, we need to understand the contribution to that comes from some of the nonlinearities in sediment transport. So, one thing to think about, if we want to try to define, say, a phenomenological equation like a kind of flux law, we need to define the scales over which this equation is appropriate. And so first I'm just going to talk about defining a length scale for applying some kind of transport law. And a classic example of this comes from groundwater hydrology and defining and the definition of a representative elementary volume. So if you want to apply something like Darcy's law, then you need to say apply it at a macroscopic scale where you can define things like permeability or hydraulic conductivity. And so that means that some kind of property like porosity of the sediment needs to be stationary. So clearly, if you look at some property like porosity over the grain scale, if you're sitting between grains, you have a porosity of 100%. If you're sitting on a grain, you have a porosity of 0. So at the very least, you need to average over enough time that something like porosity becomes stationary. And of course, though, there's an upper limit to applying, say, a kind of property like permeability, which is that when the material properties change, then you need to incorporate that. And so I have an example right there just showing, say, a permeability field. Thank you, Bill. It's going to be a long talk. So if you want to define something like a permeability field here, there are scales of heterogeneity, right, in groundwater. And so if you wanted to, say, apply a value for permeability, you want to apply it within this scale here, right, but larger than the grain scale. But then the question becomes, what if there isn't a characteristic length scale over which you can define some stationary property? Then the transport behavior itself becomes scale dependent, and the dispersion, say, becomes something like anomalous or non-Fickian, and you need a new modeling approach. And this is an area of exploding research within our community right now. So moving forward with thinking about transport laws, we also need to, say, define the coefficients that arise in these transport laws and the timescales over which we can apply them. And so a simple example of this is random walks, Brownian motion, and diffusion, right? And so you imagine that a particle experiences some kind of random kicks, and those kicks are uncorrelated. And so we look at the deviation of this particle from the 0 with time, and in the long time limit we get something like Brownian motion, which has some well-described statistics, and in the continuum limit we can apply a diffusion equation. And Brownian motion and the diffusion equation can describe the spread of the root mean square displacement or some measure of the variability, and it basically goes as the square root of time times a diffusivity. A related idea is kind of the idea of mean field theory, and I put it in quotes because I'm not talking about, say, rigorous statistical mechanics, but just to give you a general idea that imagine that you have a particle here, and the movement of this particle is determined by collisions with a whole bunch of neighboring particles. If you want to solve that problem rigorously and deterministically, it's a very difficult many-body problem. But sometimes you can basically, if you can ignore the correlations among these particles, you can replace the collisions of all those particles on this particle of interest with some mean field property, say like temperature and kinetic theory, right? And then you can just think about how something like temperature affects the activity of a particle. And so this is sometimes called a Zeroth-Order model for the fluctuations when you apply mean field theory, and that gives away the kind of a punchline in terms of the subtitle of the talk. So moving back to, say, Brownian motion, we look at, say, defining diffusivity. So if we think about Brownian motion in the context that Einstein originally derived the theory, which is thinking of a small particle, a piece of a pollen grain that's sitting in a fluid and it's being kicked around. Basically, for a small particle in a fluid of a temperature T, you can define the diffusivity, and it's defined in terms of the temperature of the fluid, a drag coefficient on the particle, and this kind of Boltzmann's constant, which is the bridge between the macroscopic spreading of some quantity, like you can describe concentration, and the microscopic stochastic dynamics. And so then you can derive something like Fick's law of diffusion, which says that a flux is equal to a gradient of something like concentration times this diffusivity. And of course, application of this sort of equation requires a time averaging. And the time averaging, for example, is that the time that you're averaging over is significantly larger than a characteristic time scale of particle motion. Now, if you're dealing with molecular behavior, that's not very difficult to satisfy. In our kind of macroscopic experience, we typically satisfy that constraint. But a question you can then ask is, what if the particle time scale is long? What if there isn't a nice separation of scales in time? Then you run into similar problems as if there isn't a nice separation of scales in space. So that's just to kind of motivate the background for the work that I'm going to summarize now. And I can kind of cast this into two key questions. And one question is, how can robust repeating geomorphic patterns persist in a very stochastic environment? Now, that's a bit of a question to bite off. You know, we can't chew all of that, especially in one talk. That's kind of one of the holy grails of geomorphology, and one of the things that drew people like me into this field is why we see repeated patterns all over the place, even when the environment is highly variable. So we're going to take the second question first, which is a little bit easier to address, which is how do stochastic dynamics arise in a steady environment? Many of you have noted the emergence of, say, terms like autogenic dynamics, which describes, in a sense, the stochastic variability that arises due to sediment transport. I'm just going to kind of stick to stochastic dynamics because I think that the autogenic processes really are just kind of mechanics to be understood. And I say there, drink it in, because some of the slides are going to get pretty dense after this. Not mathematically, just in terms of words and figures on a page. So, I warned you, right? Do you want me to go back to the last one so you can appreciate it? So thinking about applying geomorphic transport laws, I use this term loosely, a geomorphic transport law, again, to relate flux to something that we can measure. And so a classic kind of geomorphic transport law is a bed load transport equation, which links something like the mean sediment flux to a mean shear stress. And so, of course, if we want to apply some kind of bulk transport equation like this, then the bed shear stress has to be steady in time, which again means that there's an averaging time that we need to deal with. So you can, as you well know, if you look at a turbulent velocity time series, it's fluctuating about. If you look at the power spectra of a turbulent velocity time series, and I'm plotting this in time space rather than frequency space, you see this kind of turbulent cascade right here, and basically there's an increasing variance of the velocity with the increasing amount of time that you measure it over. But eventually this variance saturates at some characteristic time scale that we'll call Tx. And so this kind of saturation timescale really is just the mixing timescale in the system. So if, say, you have a flow in a river of some depth L, you can expect that there will be eddies of all sizes up to the size of the river itself. And the timescale associated with the largest turbulent fluctuation will be associated with the timescale of turnover of that largest eddy, which can be defined in terms of the length scale and the average velocity. Of course, the bed stress should be uniform, which means that you need to average appropriately for the channel and roughness parameters. Well, what about this parameter K and this critical shield stress? These two parameters are either known or suspected to be dependent on quite a number of things, like turbulence, the roughness of the bed, which affects things like form drag and pockets and things like that, and indeed the grain properties themselves. And by grain properties I mean, you know, rounded versus angular, and those sorts of things. We know, and this is an area of very active research too, that the critical shield stress for initiating motion of grains varies by more than an order of magnitude. And we can explain some of that variability. Some of the other variability we can't explain. So even this kind of simple concept of a critical shield stress is a frontier area in applying geomorphic transport laws. And even the exponent in this relationship is under some debate, right? But nonetheless, if we do some kind of appropriate averaging, at least within a system, we can come up with some kind of reasonable relationship between flux and shield stress. And so it doesn't mean that it's all hopeless. It just means that we need to understand where this kind of variability comes from, and maybe that's why we don't get the same we don't get agreement when we compare from one system to another. So I apologize if some of you have seen these slides in my previous talks at AGU, but you know, there's only so much time. But hopefully presented in a new context, it'll seem even better, right? So bed load transport rate is notoriously unpredictable, and this is for a variety of reasons, which many people in this room know much better than I. But I like to think about bed load transport as a system that has a probability distribution of impulses, things that can kick grains and get them to move. So if you're in a turbulent fluid, then we know that turbulent velocity fluctuations like this model from Schmeckley and Nelson can generate kicks in sediment transport rate. We know that there are collisions of grains, especially in coarse grain river systems, that can transfer significant momentum, sometimes even exceeding the momentum transferred by the fluid. And we're going to ignore variations in water discharge for now, so the changing environment, because that's just one part of the picture, and it's already complicated enough. There's a probability distribution of thresholds for entrainment. And these thresholds for entrainment, a lot of them come from the substrate itself. There are pockets of grains, and there's a distribution of pockets for heterogeneous grain size distributions. There are clusters, so several grains clumping together, and then of course there are bed forms. So, looking at bed load transport just a little bit more, we know if we look at a time series of bed load transport in a turbulent flow, like this large-scale experiment in a steady but turbulent flow conducted in, at St. Anthony Falls Lab in a paper by Singh et al., you see aperiodic fluctuations in bed load transport rate through time. If you collect the time series of elevation of the bed, you also see a kind of aperiodic fluctuations oftentimes. But you note, at least you can even see qualitatively, and I don't present a quantitative interpretation here, but I've done it. There's a correlation between the fluctuations in the transport rate and the fluctuations of the bed elevation. And this isn't surprising because we know that the passage of bed forms contributes to fluctuations in sediment transport rate. If we plot the power spectra of the sediment transport rate time series, what we see is something like the turbulence, which is that we have variance in sediment transport rate increasing over the time scale that we measure it over, but we see some saturation at a time scale Tx. And this time scale Tx, where the variance saturates, is essentially the time scale associated with the passage of the largest bed forms in the system. So if you wait for a time that is the length of the bed form times the average thickness of the bed form over the sediment flux, you encounter all the variance that the system has to offer. Now, it is instructive to look at some simpler experiments where we neglect things like turbulence. And this Charroux et al. Paper in JFM 2004, they have an annular flume where they did laminar bed load experiments, so they have no turbulence, no collisions between grains because they're viscously damped, no discharge variations, and indeed, no bed forms even. And when you look at the sediment transport rate, there's still a large amount of variability, which can only be attributed to clusters and pockets on the bed. And so, this is kind of interesting because it brings up this idea, which is not new, but which you can start to see a kind of convergence in the recognition of aging and hysteresis in sediment transport. And what do I mean by that? So, we know very well about armoring in streams. We know that if you have a heterogeneous grain size distribution and you run a flow over it, that the fine grains get winnowed out, the coarse grains kind of armor the bed, and that changes the effective entrainment stress of the bed. In experiments by Zimmerman et al., for example, where they were looking at coarse-grained heterogeneous distribution bed load transport down a channel, they started the experiment, and you observe that under a constant applied shield stress, the sediment transport flux declines for some period of time under the same stress by several orders of magnitude until it reaches a kind of steady state. And so, in these sorts of experiments, we think that the surface coarsening and clustering of grains enhances the bed stability, and so you see a decline in transport rate because there's effectively an increasing shield stress for entrainment. But we return back to these laminar flow experiments by Charroux et al., and one important detail is that in their experiments they had uniform spherical beads. So there's no roughness on the no angularity in the grains, no heterogeneity that way, monodispersed grain size, no variability. They observed the same effect, where under a constant applied stress, the flux declines by more than an order of magnitude before reaching a steady state. And look at this time scale, 5 days. The relaxation of the transport rate down to some steady state value took 5 days. And so they called this a kind of armoring, but it's not the kind of armoring that we're used to thinking about here with coarse grains on top holding the fine grains down underneath. So if you have uniform spheres, then you have to think that it's somehow related to bed packing, or some kind of rearrangement of a kind of crystalline structure of the bed, and the grains find themselves, say, with more frictional contact. But in this study, they didn't examine the structure of the bed particles. So what this brings up is this idea of a kind of aging in transport systems, which is that the sediment transport is actually altering the bed substrate by altering the organization of the bed. And altering the organization of the bed alters the stress for entrainment, which then alters the transport rate. And these timescales can be very long. This is an outstanding question, as far as I can tell, in terms of what sets this relaxation time and how the bed is actually arranging to increase its resistance to entrainment. And so when you start to consider all of these nonlinear factors, it's no wonder that bed load transport is such a hard problem. So maybe we can start to think about something a little bit simpler, say like fluctuations in a sand pile. And so if you have the everyday experience with an hourglass, you have, say, a fairly constant flux of sediment coming down onto a pile. And if you feed sand slowly enough, you know that you start to get an intermittent avalanching behavior. Basically, you build up a wedge of sediment until it exceeds the static angle of repose. The grains slide, they fail, they run up against the edge of this container, and they deposit at some minimum dynamic angle of repose. And so if you look at this nice sand system in an hourglass, you actually observe intermittent but fairly regular fluctuations in transport rate. So the avalanches have a characteristic time scale associated with them and a characteristic magnitude. Of course, if you feed sand fast enough, faster than the relaxation time scale of the avalanches, then you're going to move into the continuous flow regime. So there's a threshold here, and the threshold is the threshold of internal friction. And we can derive this time scale, this characteristic time scale of avalanche fluctuations fairly simply if we know the minimum and maximum angles of stability and the length of the system, and we impose some sediment flux on the system, QS. So in this dry system, if you just change, so there's no water here, right? If you just change the grains to make them anisotropic, you observe a very different behavior. If you have a pile of rice and you introduce a steady flux at the top and you measure what's coming out the bottom and you look at a time series of sediment flux, it's very intermittent. It's very irregular. It's not periodic at all. So if we plot the power spectra of this, just like the topography, just like the sediment flux in bed load, just like turbulence, we see a kind of regime where the variance is increasing with the amount of time that we measure it over, but it saturates at some time scale, Tx. And so the rice has a strong anisotropy to it. And the strong anisotropy basically introduces two things. There's a distribution of thresholds for failure because the grains can randomly lock up in more or less resistant configurations. And of course, there's also friction. These grains don't roll. And so the only kind of dynamic you get is this friction-dominated effect where no grains move until an avalanche occurs. So the transport is intermittent and irregular. Nevertheless, there is a kind of characteristic time scale, this time scale of rollover, which is associated with the time it takes to fill the critical wedge of sediment. And so there's a similarity, even though it's somewhat more unpredictable. And of course, if you feed rice fast enough, you're going to recover continuous flow. So now I want to move into the realm of continuum equations, of phenomenological equations, and try to relate them to, say, some underlying stochastic process. And I want to do this by examining the diffusion equation for 1D depositional rivers. Now, the diffusion equation has been much maligned lately in terms of transport on hill slopes and things like that because we observe that it doesn't describe the full range of behavior that we see in terms of nonlinearities or non-localities. When we think about hill slope diffusion, it's kind of a phenomenological equation that is not maybe resting on a solid physical basis. We just kind of heuristically suggest that diffusion governs hill slope creep. But that's not true everywhere. And Chris Paola showed us in a couple papers that under some rigorous, all be them constraining, but nonetheless fairly reasonable assumptions, we can derive a transport equation that has the form of the diffusion equation. But it's not a kind of heuristic suggestion. It actually falls out of the transport equation. Say, if we accept that rivers are threshold rivers that organize around a constant shield stress, steady uniform flow, some kind of total load equation, a bed load equation, and a flow resistance equation where for simplicity we say that the coefficient is constant. We're looking at evolution of rivers over geologic time, and of course we know that transport isn't happening all the time, but only during big transport events. So the last bit here is introducing a kind of intermittency factor, which integrates over the amount of time that the sediment transport is actually occurring. And if you do this, you can arrive at a relationship that says that the flux is equal to the slope times some diffusivity, and this diffusivity has embedded in it the intermittency, the transport coefficients, the water discharge, the flow resistance, and a relative submerged density. We apply the conservation of mass equation. We assume that things like this don't change in diffusivity, and we get a diffusion equation. And of course, we have a subsidence term in there if we're in a depositional environment. Then the diffusion equation, as we well know, has an equilibrium timescale associated with it. So this model works reasonably well in several different environments. And this was shown by a really nice paper by Parker et al., and actually a series of papers that was continued. I think Whipple et al. In 1999 followed up, where they applied this sort of equation to model the evolution of a delta, or a fan, in a mine tailings basin. And the basic idea is that there's a slurry of water and sediment coming in at the top, and it's depositing to build this very nice conical fan right here. But we know when we look at the fan surface that it's not covered with water all the time. At any one time, the water only covers some fraction of the fan surface. So this channel has to sweep back and forth through time in order to fill space. And so if we want to apply something like the diffusion equation, then we need to average over the timescales of channel motion so that we can say that, in a sense, the channel is everywhere all the time. And if we do that, we get the diffusion equation, or something like it, reproduces the profile of, say, a fan pretty well. But then we can ask the question, well, when can we apply the diffusion equation to model the evolution of something like a river delta or an alluvial fan? And in order to answer that question, we need to answer the question about how rivers fill space to make a fan. And one way that rivers do this oftentimes is the process of avulsion. And so here's an example of the Kosi River fan. The Kosi River comes out of the Himalayas. This is the Ganges down here. And this whole wedge of sediment right here is the fan. And here's a map of the current channel path and the former channel paths on the Kosi. And so the Kosi River has avulsed, say, every 25 or 30 years, migrating across the fan. And this is an example of an avulsion caught in the act, where a levee was breached up here and the flow spilled out into a bunch of formerly abandoned channels. And we can study this process in the lab, of course, by making a very small river delta, which allows us to speed up time, and we can make a delta in about a day. And this is work that's conducted by my graduate student, Meredith Reitz, in a tank here. It's basically just a fiberglass tank that we got from an aquaculture company. We feed in a steady supply of water and sediment to the system. From up here, you're looking down in plan form. If you're wondering why there's two colors, we introduce a bimodal grain size distribution, although that's not really key right here. But the black are coarse grains that travel in bed load, and the white are coarse grains that travel only in suspended load. And we take images of this fan every 2 minutes, and we can take some topographic scans. And what we observe is we can observe the timescale of this avulsion process. So if you plot how, say, the mean radius of the delta grows through time, that radius grows like the square root of time, which is what we expect from the kind of diffusion equation. But you notice a couple things. First of all, it takes a couple hundred minutes before this converges to the solution of the diffusion equation. And also, if you remove that trend, you see that there are periodic fluctuations on top of this diffusive trend. And so those periodic fluctuations of the shoreline migration are associated with channelization and flooding. During periods of channelization, we see that sediment's transported through the channel, and it progrades the front of the delta, and the shoreline bumps out. It bumps out until the channel gets lower than some critical slope. It deposits and fills with sediment, and it floods. And then when it floods, it picks a new channel. Now, we're not the only ones to have seen these dynamics. The Jurassic Tank team, I think, really pioneered a lot of the studies of these autogenic dynamics on fans. There's some really great results from the Exeter team and the Utrecht team and now the UT team. So there's a lot of people that are interested in these dynamics. So what's interesting, or one thing that's interesting about these fan dynamics, is that they're essentially fluctuations around an equilibrium slope. And so this is just showing you an example of the traces of the shoreline through time. So areas that are bold, black, are areas where the shoreline sat for a while, and then you can see it bump out here, it bumps out here, and it bumps out here and sits there for a while. So we make a plot of the slope itself through time. And you can see that there are slope fluctuations. And a few things to notice about these slope fluctuations. First of all, they're asymmetric, or they're skewed. Second of all, there appear to be two characteristic timescales. There's a small timescale which we've determined to be the timescale of channel avulsion, and then there's some larger timescale. Well, because most of the avulsion cycle is taken up by filling a channel with sediment, we can estimate the avulsion timescale, the expected avulsion timescale, as essentially being the time it takes to fill a channel of depth h, width b, and length l with the imposed sediment flux, Qs. And so this is very similar to what we see with, say, the sand pile. What's remarkable about this simple timescale is that when we put the calculated avulsion timescale from this against the measured avulsion timescale, we get a good agreement, not just in our experiment, but in other experiments that have been done. And if we're bold enough to extrapolate in the field, where painstaking and beautiful measurements of large deltas like the Mississippi and Rhine Meuse have actually determined the average avulsion timescale, we can plot the calculated one against the measured one and we get a pretty good agreement there, so over orders of magnitude. So we think we have a beginning of an understanding of this kind of the timescale governing the stochastic fluctuations of the channel movement. So how does the channel fill space, however? It fills space by path selection and reoccupation. And so what this map right here is a map of cumulative inundation over an experimental run of about 300 minutes. So the areas that are black are areas that have been visited by water many, many times. Remember that the avulsion timescale is about 20 minutes, so we're looking at least 10 avulsions. So if you see areas that are showing up dark here, it means the flow has returned there over and over and over again. So the channels actually return to previous paths. They like to go places they've been before. Once we establish a network of channels, say about 4 or 5 of them in the experiment, the flow oscillates indefinitely among those channels. And so there's a kind of aging phenomenon in the evolution of this fan as well. Basically, as channels form by the avulsion process, the flow is more likely to return to those same channels than it is to visit someplace new. That's interesting in and of itself. Why would the flow return to channels that it's been in before, even if those channels have filled completely with sediment? Well, in answer, we have a tentative answer, one that we're trying to demonstrate now, which is that the channels represent coherent downsloping paths. So this is an SRTM topographic map of the COSI fan, and what we've done is just extract the paths of steepest descent from this fan. And the paths of steepest descent are indeed the actual channel paths that have been mapped in the past. Many of these channels have no topographic expression in terms of being a depression, but they have a topographic expression in that they're a coherent downsloping path to the bottom of the fan. So we think that the flow returns to these places because these are places where if you put a drop of water at the top, it can run all the way down to the bottom. And so how long then does it take for the channels to fill all space and make what looks like a cone? And what determines this time scale? So what I want to try to do is a very, very crude and an empirically closed, but nonetheless instructive example of linking some stochastic dynamics at a small scale to a geomorphic transport law at a large scale. And so I want to relate the avulsion dynamic to the phenomenological diffusion equation. So we can take a radially averaged fan profile and plot it. And we have this slope right here. And if we presume that we have that transport can be described by a diffusion equation, we know what the flux is that we're putting at the top. We know what the slope is that results. So we can back out a diffusivity. And we can back out a time scale, an equilibrium time scale for a delta of a given size. Another thing we can do then is look at how this channel fills space. And this we followed in the example of a paper by Kazanakli et al. Where basically the idea is that you look at how a channel fills space through time by the area of the fan remaining that has never been visited by the flow. So in the beginning of an experiment, 70% of the fan, say, is dry. And then you look at that proportion that remains dry and has never been touched by water, and it declines through time. And what we find is that you can describe this decline roughly by a kind of harmonic decay function. And this was introduced by these guys. And the harmonic decay function looks like this. It just says the fraction remaining dry is equal to the initial fraction that was dry over 1 plus time divided by some constant. So if we just take this equation and we basically stuff in our measured avulsion timescale, without doing much acrobatics, we recover a curve here in red that is not a bad approximation of this blue curve. Now, you'll note that it underfits here and overfits here. You can fit this thing slightly better with a power law equation. But what you gain in using this harmonic function is that it can be described with only one parameter, which is nice. So for simplicity, we'll stick with it just because it allows us to do some analytical things. What's interesting is that it definitely doesn't fill space exponentially. If space filling by a channel was a random process without memory, then you would expect it to rapidly fill space. And so the space filling is much more slow than random. And of course, as it approaches 0, it gets longer and longer and longer. So you can ask some questions, say, like, how long does it take to visit almost all of the fan? Say 95% of the fan. And the time it takes to visit almost all of the fan is about 200 minutes. So we can take our avulsion timescale, and we can take this decay curve here, and we can essentially estimate what we think the diffusivity should be at the large scale, derived from the avulsion timescale and the memory effect that are encoded in this expression. And so that means that we can arrive at a diffusion equation, and the diffusion equation is applicable as long as the timescales are significantly larger than the avulsion timescale itself. And for these experiments, that's about, say, 10 times the avulsion time. So one thing that's implied by this, though not proved yet, is that at timescales smaller than this, the system actually cannot be described by diffusion because there's a memory effect, because the flow is returning to places it's been before. But once you wait long enough, you're averaging over the timescales, and this memory effect is no longer relevant, and you can recover something like the diffusion equation. So I have really good pictures of my grad students, right? Until they send me better ones, I'm going to keep using these ones. So Raleigh Martin's been doing some work in our lab on, on particle transport, bed load transport, and diffusion. And I'm just going to take a little bit of a speculative flight of fancy and discuss another kind of space filling, which is something like random cluster growth of particles in low-stage bed load transport and the diffusive coarsening. And so if you have a bed that is rough but a fixed bed, and you introduce mobile grains slowly and you let them be transported down the channel at a low transport stage, which is typical of a lot of bed load streams, what you observe actually is that it makes sense. If a grain is rolling along and it runs into another grain, it's very likely to deposit, right? And so if you look at the growth of clusters with time, you can see these kind of little islands that are starting, and they're growing and they're growing and they're merging with each other, right? And so there's this kind of cluster growth, and they're coarsening as they merge with each other. And so it kind of suggests that maybe there's some, if the transport of grains is related to how many grains are deposited on the surface, then there might be some, you might expect that the cluster growth might lead to some kind of percolation transition. And so I quote here from Sornet that a growing body of work has shown that percolation is suitable as a first approximation as soon as the property of connectivity is the dominant mechanism. So you imagine that we have random cluster growth here, and these clusters are isolated. They don't connect to each other to form a cluster that goes across the entire domain until some critical density. And at some critical density of grains, those grains will all link up, and there will be a cluster that spans the entire domain. And once clusters expand the entire domain, then other grains coming in are bound to be stuck to these clusters, right? And so you might wonder whether there's some kind of dynamic transitions that occur at a percolation threshold for a system like this. And so, this might be applicable to cluster growth in gravel rivers. I don't bring this up because we have an answer, just as much as suggesting an idea that the connectivity of these grains, if the connectivity of these grains affects the transport of future grains through the system, then we might see something that's reminiscent of percolation, even if not exactly. So, for low-stage bed load transport, clusters trap grains. The clusters grow randomly. At some critical density, you might expect that these clusters span the entire channel. If the clusters span the entire channel, then they become a very efficient trap for other grains coming down the channel. And so this is just a wild guess, but you might predict there to be a bimodal density of grains covering the bed, of alluvial grains covering a bedrock channel, due to a potential kind of runaway alluviation that might occur once the density of grains covering the bed exceeds some critical density. Now, of course, there's other things going on. This bimodality might be enhanced because if you're at very low density of grains, an isolated particle is very easy to move, so it may not be likely at all to stay within the system, and it moves on by. And so I'm sorry, Joel, at all, I'm not butchering your paper. This is not anything they suggested. It's just a guess of mine that there's this prediction that maybe there's a bimodality in alluvial cover. And so Johnson et al. Went out to a bunch of rivers in the Henry Mountains, or a couple rivers in the Henry Mountains, where they went downriver and they looked at the percent of bedrock exposed. And what you find is that you have anywhere between 50 and 100% exposure of bedrock, but once you have less than 50% bedrock exposed, or maybe more than 50% alluvial cover, it seems that you don't like to exist very much in this phase space, that you might run away completely to 100% alluvial cover. At the very least, both of these tributaries show that alluvial cover is bimodal. You tend to have a lot of alluvial cover or a little alluvial cover and not very much in between. So, returning to the second key question now, how can robust repeating geomorphic patterns exist in a stochastic environment? As I mentioned in the beginning, this is not a question that we can really tackle here. We can barely even begin to tackle it here. But I just want to speculate on one way in which geomorphic patterns might be robust to environmental perturbations. And so, I want to talk about the idea of noise-induced stability. So, you know, Chris Palin likes to talk about turbulence as a metaphor for geomorphology. And when I showed up as a naive graduate student at MIT, and I sat next to my office mate Joel Johnson, and I was talking about Dolomite, the 1970s movie, you know, the action movie, and he said, "What are you talking about? You know, you're talking about Dolomite the rock." I said, "I bet if you do a Google search that Dolomite the movie is far more popular than Dolomite, you know, the rock." And I was wrong. I was that naive, and of course, in that case, geology won, and Dolomite, the movie, was way down on the list. But when I did a Google image search on turbulence, to my surprise, this was the first thing that showed up. Now, it is sort of appropriate that turbulence is the metaphor for geomorphology because the name of his hit album is notorious, as turbulence is in geomorphology, and perhaps even more foreboding, Turbulence's other album is called The Future. So, ponder that. So if we think about, though, turbulence and inertial flows, of course, we now return to this power spectrum. We know that we have a non-steady regime of the turbulent energy cascade, but at long time scales, we have kind of a steady regime where the variability saturates. What happens if you take an isotropic turbulent flow field and you perturb it? And people in the field, in fluid mechanics, call this kicked turbulence or modulated turbulence. The basic idea is that you have an isotropic turbulent flow field, and you start introducing periodic perturbations either in momentum or in flux at the boundary. And you measure the response of the turbulent velocity flow field, and you ask the question about whether the system feels those perturbations. Well, as it turns out that if you kick a turbulent flow field with a periodic perturbation that is at a time scale longer than the mixing time, the kick is slow enough that the system can respond, and it responds, you're in a quasi-steady regime, and the system responds accordingly, and you can see that kick in the response of the system. However, if you kick the system with a perturbation at a high frequency, and it's buried within this turbulent mixing regime, then that kick gets smeared across a range of scales. So for turbulent flows, they actually are insensitive to environmental forcings at time scales significantly smaller than the mixing time. And this is in contrast to low Reynolds number flows. So, how about sediment transport systems? Well, we know that we get sort of fluctuating behavior and power law behavior. For example, landsliding. And I have Stark and question mark there. I've used this power law distribution of landslides a few times, and it's probably from Colin, but I'm not sure. So I apologize whether it is or it isn't, because I'm not sure who to give credit, but, you know, thank you. And so there's typically a power law tail to the distribution of magnitudes of landslides, and there's a similar behavior seen in the rice pile, where you see a power law tail to the distribution of landslide magnitudes. So we can actually create, and I was not the first to do this. There were papers by Christensen et al. And Frett et al., and we've just used their model, where a model for the rice pile, they say you can have a one-dimensional model, a kind of toppling model, which is like the sand pile model, except that you introduce a randomly varying critical slope, which is meant to reproduce the distribution of thresholds for failure seen in the anisotropic medium like rice. And the numerical rice pile produces behavior that is like the real rice pile, and of course you get an intermittent transport rate, and if you plot the spectra, you get the variance increasing with time and saturating at some timescale Tx, and this is the same characteristic timescale that we see in other places. So this got Chris Paola and I to thinking about how systems that exhibit fluctuations in transport across a range of scales might respond to periodic environmental perturbations, and whether this might be something like the turbulent flow example. And so we take the numerical rice pile model and we introduce to it, rather than a constant input of grains, we introduce a periodically varying input of grains with a period t and a magnitude m. And of course, if we vary that perturbation slow enough beyond this timescale tx, then we're in the quasi-steady regime. However, we find, just like the turbulence example, that if we vary the timescale, if we vary the perturbation at a timescale buried within this noise, that if we measure the output of the system and we plot the spectra, we see no statistically recognizable response of that perturbation. And so it does appear, at least from this very simple numerical model, and it remains to be demonstrated in a real physical system, that the internal noise of sediment transport may buffer the system against external perturbations, at least perturbations over a certain frequency range. Of course, there is a magnitude effect. If we introduce perturbations with an amplitude that is so large that we overwhelm completely the buffering capacity of the system, then we will pass that signal out the other end. So this raises some interesting questions for us to think about in terms of landscape evolution and how things like discharge variability or climate variability actually propagate through systems. Because in a real sediment transporting system, say like a nice cobble or bouldery river, you expect to have noisy transport even if the discharge was steady. But of course you have noisy perturbations in this system. So if we look at an example of just the a frequency magnitude plot of discharge, and this just comes from a river in Puerto Rico, they can be heavy-tailed as well. So we can have heavy-tail distributions and event magnitude of discharges. Of course, if we look at a time series of discharges, highly intermittent as well. So we've got noisy transport getting kicked by a noisy signal. So I don't have an answer for this. This is a question that I think is interesting for us as a community. That if you say you have a system like this and you introduce a big flood wave, we know that big floods tear up rivers, that they move sediment. However, there are lots of reasons that the transport within the system could become decoupled from that big kick. For example, we have the formation and breakup of clusters, and if you imagine a grain that gets picked up by the flow, it can move through the system until maybe it hits an immobile element and it stops. Or maybe you have low stage transport, but this particle hits a cluster and it makes it break, and it triggers a large collapse. Then, if we're looking at the transport of grains, these grains aren't just being moved by the flow, especially if we're in a coarse grain system. They're being moved by being bombarded with other grains as well. So there's momentum transfer from grain collisions. And finally, there's things like grain inertia, the fact that the vector of grain transport doesn't necessarily follow streamlines, especially true for coarse particles. And so all these factors may act to decouple grain motion from fluid flow. And so pulses of, say, from floods or from sediment may be broken up by the stochastic transport dynamics itself, so that maybe, just maybe, there's some robustness to these rivers simply because the whole things don't just get all the grains don't get picked up and flushed out by a flood, but they kind of break up the pulses that we introduce into the system. And so, I don't really feel like, especially in front of this community, that I'm in a position to discuss research directions that we should take. So they're more like research directions that my students might think about taking. I don't know, right? But we know that in a variety of sediment transporting systems that there are thresholds of motion. There are thresholds of motion for picking up grains in bedload, for landslides, and indeed for avulsions in a fan system. And so these thresholds of motion introduce a kind of stick-slip dynamics in the sediment transport, and so there's a kind of stochasticity that arises. Nevertheless, there are characteristic scales in this stochasticity that are imparted by the physical scale of the system. And I don't think that we understand all these scales. I think we're just beginning to look for these scales. But for some of the systems that we've looked at, this critical time scale can be understood fairly simply. An area of research that I think is really exciting is this idea of aging in landscapes. Because we know that the order or disorder of the substrate affects its ability to be transported, but we're also learning now that transport itself changes the order or disorder of the substrate, which changes its transportability. And there are relaxation timescales here that we really don't know very much about, but that are undoubtedly very interesting. And we also see this kind of aging on the fan, where the more we create channels, the less likely we are to create more channels. So we think about geomorphic transport walls. There's some really exciting opportunities to link the kind of smaller scale stochastic dynamics to the phenomenological equations. And in fact, there was a hydrology session on stochastic transport and emergent scaling, where there were some really fantastic talks and thought-provoking talks thinking about a kind of statistical mechanics approach to geomorphology. And this is not something that I'm an expert in, but something that other people in the community are starting to tackle kind of theoretically. And one thing we know is that if there's no separation of scales, then the stochasticity in the system must be dealt with. And some in the community are starting to come up with non-local transport equations, fractional advection dispersion equations, and the like. And this is really something that's emerged just in the last few years, and it's been really exciting to watch. And so, obviously, I'm really excited about the future of research and the challenges in front of us. And, you know, I like experiments, but I think that there have been a few really important papers recently that have really provided us with the justification that we need to move forward with small-scale experiments where we can observe everything and have some confidence that we can relate these experimental dynamics to real physical systems. In experiments, we can both measure and perhaps derive characteristic scales of channels, of fluctuations, of valleys, and things like this. We can also observe directly the stochasticity. We can measure the variability in flux. We can track individual particles and see what they do. And of course, in experiments, we can explore the stability question, right? Because we can take a landscape, we can evolve it, then we can kick it however we want. In terms of theory, as I mentioned, there's some really exciting beginnings of a kind of statistical mechanics approach to looking at sediment transport, and some advances in, say, fractional transport equations. What I see is that in terms of understanding the stochasticity and ways to deal with it, we're going to be borrowing a lot of methods that have been used extensively in hydrogeology, in granular and soft matter physics, and even in materials science. And so what I want to close with is there are far too many people for me to acknowledge. I mean, I think everybody in this room almost has contributed ideas that have gotten me excited in the field. And so for all my colleagues, I'm sorry I can't mention you, but the people that I need to mention the most are my mentors. Basically the people that taught me that science was fun. David Morg was my PhD advisor, and from the first day that I showed up, well, he was very serious about having fun, I'll say. That's Kyle Straub, and that's Paul Heller. And the one thing about David is his unfailing optimism that things will work. And when they don't work, he's equally excited because they didn't. And, you know, if I've learned anything, it's how to deal with that adversity and embrace it. Also, Chris Paola has been hugely influential on my thinking. I was fortunate enough to do my postdoc with him. I've learned from him. I have to mention Aaron Packman because my very first research experience was in his laboratory as an undergrad. And Claire Welty, she's a groundwater hydrologist. I don't know if she's in the room, but as much as I thought that I was determining my own outcome, she said, "You are going to do your PhD at MIT," and that's what I did. And so she knew better than me. In addition, I've had advisors. I've interacted with Effie and Vaughn extensively. Maria Zuber, John Grotzinger, Dan Rothman, all of these people have contributed directly both to my thinking on these problems, but also just to my advancement in science. And I can't blame any of them for any of the confusion or mistakes or just wrong things I've said in this talk, but I can thank them for getting me excited. And finally, you know, I'm in my 4th year as a professor, and I have a phenomenal group already, and I'm incredibly fortunate. Some of these people have contributed directly material to this talk, and others have just been in the group meetings where we develop these ideas. So Kim, Federico, Raleigh, Meredith, Colin, thank you guys. And thank you everyone for listening. No, I can't go anywhere.
Thank you very much, Doug. I just want to say that I'm sure you noticed this too on slide number 17,413. There was a mistake.
There were only 22 slides.
I'm sure that Doug would be happy to take some questions. There are microphones in the middle of the room.
Just remember, don't take this too seriously. These are just some ideas, right? Nobody. God, this is going to be easy. Okay. Can I go home now? Oh, I can't see.
Thank you, Mauricio.
Oh no, that's Gary's voice, isn't it?
Oh, it's me. I can see you, but you can't see me. The talk was very inspiring, and I'd appreciate your comments on something that has been of interest to me in watching experience back from my early days at the University of Alberta on braiding streams up till then. And when we tried doing larger scale morphodynamic models, we usually get some kind of estimate of flow, get some kind of shear stress, and get some kind of sediment transport rate and compute how the system evolves. And yet a lot of what's really fun to look at is fun to look at because the water is where the sediment isn't, and the sediment is where the water isn't in terms of movement. And that the fact that sediment transport and water don't correlate that perfectly allows it to build lots of fun structures. And of course, that's a kind of, if you want, it's autogenically built into the system.
Yeah.
But I thought you might have some enlightening comments about that kind of built-in disjointness, which I think is a kind of noise that makes interesting structures.
Sure. I mean, of course, as you know much better than I, the fact that the time scale of evolution of these systems is typically significantly slower than the movement of water is merciful in a lot of ways, which has allowed us to develop these kinds of theories just from a separation of timescales. But I suspect what you're talking about, since you know about that very well, is some of the other stochastic elements that arise. And I mean, I can't speak about what is most important for the community, but one of the things that I have been really interested in is the mirroring when we look to dry granular systems where we see some very similar stochastic dynamics arising in the absence of fluid flow. And so that certainly doesn't account for all of the variability, but I mean, in a lot of the grain size segregation that we see, a lot of the structures that get built and the resistance to movement, these kind of avalanching dynamics, I think that we've put a lot of energy into understanding the fluid because the fluid typically supplies the momentum to moving sediment. And we're beginning to put a lot of energy into understanding the grains. But I would say that the granular physicists we have a lot to borrow from them in terms of understanding what happens when grains interact together to produce sorting patterns, to produce variability, to produce structure. And I think that some of that interesting decoupling and stochasticity comes from that the fluid shears the bed and moves the grains, but then the grains interact with each other. And that interaction of grains with each other is something that can't be ignored. Is that okay?
It's more than okay.
Doug, in your talk, yeah, it's alive. In your talk, you mentioned a number of unexpected sources of stability or stabilization in these systems, which in some respects simplifies behavior and others complicates it. In real systems in the field, and we were very well aware of this when we were doing the steep channel work to which you made passing reference, there's a bunch of things related to life forms that do strange things to the physical system. And have you thought about systemically introducing life forms into this picture? And I'm thinking not just of trees growing on a stream bank. I'm thinking of things like microbiota that glue rocks together in the bed of river channels and things like that. Because they have their own, usually reasonably well-defined timescales for development.
Can I say no? No, I mean, in a sense, we had, I think about it all the time. I struggle with how to include it directly into research. And I think this is something that a lot of the Earth surface processes community is faced with, right? Which is that biological agents affect transport and geomorphology in a variety of ways. I think the most interesting interactions that we expect to occur should be when the timescales are comparable to each other. In other words, if there's a strong separation of timescales, then one thing is going to be slaved to the other. But where I expect to see the most interesting dynamics to emerge possibly is, say, when the growth time of some bugs growing on the rocks is comparable to the timescale over which those rocks are perturbed, or when the vegetation growing on a stream bank is comparable to the timescale of erosion of that bank, where we may see emergent new structures that represent a coupling. Because in order to have a feedback, they don't have to be at the same timescale, but I think you're most likely to find interesting feedbacks. Now, I think that we're in the stage right now where proof of concept is really important. In other words, that we can't bite off the whole enchilada right now, but we should be looking for systems where interesting behavior emerges. And I mean, I can give a plug for work that we're doing on, and it's building on work that others has done for sure, but we've been doing a lot of work in White Sands on vegetation growth. And a student of mine presented a talk, Meredith Wrights, on the inversion of Barkhan to parabolic dunes. And there's an interesting thing that occurs there, which is that despite the fact that transport and vegetation may interact in complicated ways, even through form drag and all this sort of thing, we really observe a kind of simple threshold crossing where as long as the landscape is evolving fast enough, the plants never take hold. And there's a point in the dune field when the transport rate just becomes low enough that it's a threshold crossing and the dunes go from 0 coverage to 100% coverage over a very short time. And so there are these kind of threshold crossings to look for that are associated with the timescales of landscape evolution compared to the timescales of plant growth, where dramatic transitions, almost phase transitions, occur. And I think those are really exciting. And personally, I'm in the process right now of identifying those. And we've been looking at work and trying to organize the community, like the MyRes meeting that some colleagues of mine and I organized a few years ago, looking for these sorts of problems. So certainly I see a lot more of that in the future. That's it?
Are there any more questions?
All right.
Before I ask you to thank Doug, let me remind you of a couple of things. First of all, the gilt-edged certificates, one of which goes to Doug for the Leopold Award, and the other one goes to Bill Dietrich for the Gilbert Award. Remember, these are up here with a pen to be signed on the back, if you would like to do that. There are at least 2 EP sessions that I know of to follow today. There's a source to sync one in MS 310, and the authors of that session would very much appreciate an audience. There was another session, an EP session in here too. It's mine, Terrestrial Response to Rapid Climate Events. So with that, let's thank Doug once more very much.